Okay, section 3 is going to get into what do these graphs, what do these polynomial functions look like when you are actually graphing? What do the functions look like when you're graphing? Now, I'm concerned with end behavior. We talked a little bit about that yesterday. And roots. And the only roots I really care about, honestly, are the real ones. I care about the imaginaries, but as far as my graph goes, the real ones are all you're going to need to worry about. So, again, we talked about how do we name these functions. Degree of 1 is linear, so you're going to get a line when you graph it. Degree of 2 is a quadratic, which means you're going to be a horseshoe up or a horseshoe down. Degree 3 is where we start to see some options here. It's a cubic. Again, if it's third degree, it's odd. You have to end and start in opposite directions. But you have a couple of choices on what the graph looks like. It can be a cubic like the parent graph, y equals x cubed here, with inflection, or you can have one real and two imaginary roots, which give you this peak and valley type of thing. So that can happen also. And it can go in opposite directions. It can start up and end down. But they have to end and start in opposite directions. Just like the quadratic, even has to end and start in the same direction. So when we go to the next even, quartic, it's either both up or both down for the end behavior. And you could have, like the parent graph, y equals x to the fourth, or you can have imaginary roots, which gives you this little wiggle somewhere above or below the x-axis. The wiggle part is not super critical to me if they're imaginary. If you go back to a quintic, fifth degree, then you end up in opposite directions again, and you can have some wiggles in between, depending upon your roots. Everybody good here? Yes, sir.
So since you know if it's like a quartic or a quintic, you know how many roots you're gonna have.
Yeah.
Then would that will tell me how many like wiggles would be in between?
It will control that for us, yes.
Okay.
So if you bear with me, we're going to go into look at just how do you tell? You know, how many times does it bounce? How do we know that? And what do we know about the roots? Those are the things that we're going to get at today. Again, these graphs are more of a sketch than a graph. Okay, they're much more of a sketch than a graph. What I don't want you to have to do is T-chart things. Right? That's what we're trying to avoid. So for an even degree function, like an x squared, an x to the fourth, x to the sixth, and so forth, x to the eighth, an even degree function, if a is greater than 0, what's the end behavior look like? Both up, touchdown. So even degree a is greater than 0, we expect to see something like this in the graph. If it's even degree and a is less than 0, what do you expect to see for the end behavior? Both down. Okay? Whatever that symbol means. I thought it was goal in soccer, right? Okay. Would be this. So a is less than 0. We expect end behavior for an even degree function to be both down. We talked a little about this again yesterday. Odd degree, if a is positive, which way do you expect the end behaviors to be? Positive. So we're going from left to right, we're going up. So on the right-hand side, which way is it pointing?
Oh,
down. And on the left-hand side, up.
oh, your left.
Yeah.
It's
No, your left. Your left is pointing
down.
right. Didn't I do that?
You said right. Switched it. Yeah.
So let's say it again then. If a is greater than 0 and it's odd, on the left, we're pointing down.
Yes.
On the right, we're pointing up.
Yes.
Okay. Frank, you have no credibility. You're just waking up. I don't know whether you're telling me the truth or it's all
I got a
just...
class back.
Right. Okay. So if it's a negative for A, then on the left we're going to be pointing up, and on the right we're going to be pointing down. We did this yesterday. That's just end behavior. Now we have to figure out what's going to happen in between. Okay? What's going to go on in between. Now, first thing you need to ask yourself, always, is what's the degree? Now, what form is this function written? Yeah, it's kind of an intercept form. What's another word that we could use? Yeah, your favorite F word. This is factored form right here. Now, in factored form, if you were to get rid of all your parentheses, what would the power on the x be? The biggest power on the x be if you got rid of all your parentheses? 6. That's your degree. How do you know it's 6? Well, this is an x squared. This is an x to the imaginary 1 power. And this is an x cubed. What do you do with your exponents when you're multiplying? Add them. So this would be x squared times x to the first times x to the third. That's a 6th degree function. Because it's in factored form, you also should be able to identify that the roots of the function are going to be 3, -4, and 1. 3, -4, and 1. So 3, 0, -4, 0. I don't know why that says a half. Well, I do know why it says a half. This should be a 1 right here. Then we will replace it with a 1. The power on the factor that gave us the root 3 is a 2. That means that 3 is a double root. The power on the factor that gave us the root -4 is a 1. That means -4 is called a single root. And the power on the factor that gave us the 1 as a root was a 3. That means 1 is a triple root. If you were to expand this, you would get y equals x minus 3 times x minus 3 times x plus 4 times x minus 1 times x minus 1 times x minus 1. If you were to expand that, that's what you would get. And you can see that -3 is a factor or a root twice. That -4 is or 3 is a factor twice. -4 is a factor once. And the 1 appears as a factor 3 times. That's how we know that these are going to be single, double, and triple roots. If a root appears an even number of times, like a double or a quadruple, something like that, the graph is going to be tangent to the x-axis at that root, at that point. That means the graph will bounce on an even root. It will not cross through the x-axis. It'll go up and like hit the ceiling and then bounce back down. Or it'll come down to the floor and then bounce right back up. It can't cross through with an even root. A double, a quadruple, and so forth. If it's an odd root, it appears an odd number of times, the graph will cross through the x-axis at that point. If it is a single, the graph goes straight through. If it is a single, it is going to go straight on through, no wiggle, no nothing. If it's a triple or 5 or 7, any other odd root, the graph will inflect, which means it will wiggle through at that point, and I'll show you exactly what that looks like in a moment. Singles for odd roots, single, straight through. Any other odd, 3, 5, or 7, it's going to inflect when it goes through the x-axis. It will inflect at that point. Evens, if it's an even root, it will bounce. In order to be able to identify if you have an even or odd root, it has to be in factored form, or you have to P and Q it. And use the rational root theorem. Everybody good here? So when we look at sketching the graph, this example is already in factored form. So what I'm looking for is identify the roots. So what are the roots for this function? -1, -1, 0. What else? 1, 0, and 2, 0. It is. Doesn't matter, it's still a root. After you do that, determine if single, double, etc. roots. So, Lauren, which one was the triple? 2 zeros, a triple root. What about -1, 0? Single and another single. What's the degree? Okay. So use the degree and leading coefficient to determine what do we determine with those two? In behavior. Plot roots and graph. The only points I care about on the graph will be the roots. Even you OCD people don't want to go making T-charts on this stuff. So when we're going to graph this, what's that? Leading coefficient. Leading coefficient. So if we plot these roots, we're going to be at -1, 0, we're going to be at 1, 0, and we're going to be at 2, 0. The leftmost root is right here. If you look at the degree in the leading coefficient, what is the degree? The degree is 5. And the leading coefficient would be 1. And the number itself doesn't matter. What matters? Positive or negative, and it's going to be positive. Degree is 5, leading coefficient is positive. So the end behavior on the left should be going down. On the left, so from the left root, we expect this graph to go down. Okay? Now, -1, what kind of a root is it? A single. So the graph at -1 should go straight through. Graph at -1 should go straight through. Now, the end behavior on the right for a degree 5 leading coefficient positive, what should that be? Up. So we're down on the left, up on the right. So from this root, and I'm not going to connect it yet, we should end going up. In order for this graph to come up and go through the graph right here, what do I have to do to the graph in order to have another root right here? Turn around, right? It's got to do something like this. Somewhere it's got to turn around. What kind of a root is 1? What happens on single roots? Straight on through. So as we come back down, we're going to go straight through. In order to get to this root, what does the graph have to do? Turn around again. What kind of a root is 2? Triple. In a triple root, you're going to have inflection. Now, I'm going to exaggerate. If this is my root, inflection means it does this. Okay? Inflection means you're going to come up, roll over the top here, hit the root, and then turn back up. So you're kind of coming over the top like you're a left side of a parabola, and then when you hit the root, it becomes the right side of an up parabola. So we have a point of inflection right here. You need to make sure I can see that it is a point of inflection. So you've got to give me a wiggle in there somehow so that I know that you know it inflects. Straight through, inflection. I don't care how high up you go or how far down you go on these points here or how steep this is or this is. I care that you go straight through, and inflect. Whenever you have an odd repeat of root, so if the root is a 3, a 5, a 7, if it's a single, straight through. If it's a double, what happens? It bounces. And we'll look at one of those here in a second. Graphing, especially in this form, should take you about a minute tops. That's probably giving you 30 seconds to look at your work. All right. Anybody see anything questioning on this? So let me remove this just so it's not confusing anyway. That's just one inflection. Let's try another one. Okay, see how you do. Give this one a shot. Try this one. See how you do. So, leading coefficient. What's the leading coefficient? Negative. -1 specifically. What's the degree? Be careful on this. It's 3. So what does that mean for our end behavior?
Start on the left, and then the bottom right.
Yeah, so on the left, which way? Up. On the right? Down. What are our roots? 1, 0?
1, 2, 3, 0.
3, 0. What kind of root is 1, 0?
Single.
So we'll put an S here.
I'm awake now.
Yeah. And 3, 0?
Double.
That 5-hour energy drink's really working for you, huh?
Never had one before.
Really? You could do the commercial.
I could.
So 1, 0, 3, 0. From 1, 0, we have a single. What do we do with that root? Straight through. So from here, we're going to be pointing up, and we're going to come up, go through. It's going to look like this. 3, what kind of a root is that?
Double.
In order to get to the 3, we have to turn around and bounce off the 3. You cannot go through the x-axis. How many times am I touching the x-axis? How many roots did I list? 2. This is the honest to God truth. I want to tell you right now, this is what people do to me. They will come through, they'll do this. How many times is the purple touching the x-axis?
3 times.
3 times. That's great, it's degree 3, but you have how many roots here? 2 and 1, 2. I should have 3 roots. That can't be the right graph. Sometimes they will come through and just keep going. That kind of thing. Well, you only have your 2 roots, but you didn't bounce. And they're both pointing up. That means you have an even. Count how many times your graph is touching the x-axis. It is always astounding to me to watch people put in extra. They have their big points right here, and then they'll give me other places where the graph crosses the x-axis. Count them. It only takes a second. Try this one. A little more complicated. All right, here we go. Leading coefficient is 1, so it's positive. Degree 4, So that means the end behavior should be both up, up, up. The roots. 4, 0, 1, 0, 3, 0. What kind of root is 4? So here we go. 1, 2, 3, 4 is a single. 1 is a single, and the 3 was where the double was. So we got to be up and straight through here. We got to bounce off of the 3, right? So somewhere along the line, you're going to have to turn around however far down you want to go, and then straight through. So your end behaviors both up, touch down. Single root, straight through, single root, straight through, double root, we bounce. What do we do on a triple root? Inflect. So we roll it over and then come back underneath.
When you're inflecting it, does it inflect at that point?
At that point of inflection is where the two curves would meet. They would look like two, when you zoom in, it really looks like you're coming over the top. You hit the root and then you roll up and you have almost like a top left parabola and a bottom right parabola. Okay? And that's what we mean by a point of inflection. When you see the point of inflection, you know it's a multiple odd root. A 3, a 5, or a 7. Okay, let's do this one together. What is the leading coefficient? Negative, the degree. Careful. What is it? 5. So we have a 2, a 1, and a 2. The end behavior, therefore, has to be on the left, up, on the right, down. Odd, negative.
Yes.
Up on the left,
Down on the right.
right.
Yeah.
Yeah.
You get being so enthusiastic.
So for our, bless you, our roots, what are our roots? 0, 0, 1, 0, 3, 0. What kind of root is 1, 0? Or 0, 0? That's a double. 1, 0, 3, 0, double. So we have 2 bouncing and 1 straight through. 0, 0, 1, 0, 3, 0. On the left side, we're starting up and we're going straight through. So we're going to come straight through here. What are we doing at 1? Oh, that's not true.
No, it's wrong. Okay.
Thank goodness you're here. We're going to come down and we're bouncing off of the 0. We're going straight through the 1. And we're bouncing off of the 3. You OCD people can plot all kinds of points in between these roots to figure out how high up and how far down you go. I don't care. This is all I need from you. Okay? This is one of those ones you want to just keep it simple. Okay, give this one a try.
Father's check.
Okay, what are the roots? 1/2, 0. What kind of a root is 3? Double.
Single. Triple. Go.
What's the degree?
6.
6. Leading coefficient?
1.
So positive. So the end behavior? Both up. So net, we got 3, 0, a 1/2, 0, and negative 4, 0. There's your roots. So your graph on the left has got to be pointing up. What do we do at -4? Straight through. So our graph's going to come down straight through here. We have to turn around to get to the 1/2. What do we do at 1/2? Even flat. So we're going to come down, turn around. We're going to make sure we're coming over, and then we roll through. And then what do we have to do at the 4 or the 3? We have to bounce. So when we come through, we're going to roll and bounce. And our end behaviors are both up. Okay? Now, there's only one, that's it for today. But there's one curve that they're going to throw at you occasionally. You're not even going to see it. It's going to look like a fastball, and you're going to just say, oh, fastball, and I'm going to hit it, and then you're going to swing and miss. So here's what I want to show you, and we'll just take a look at it on what happens on the graph. So I want to give you an example first. We're going to do x minus 2 x minus 2 times x plus 3 squared. Okay? X minus 2 times x plus 3 squared. And when we graph that, you had a double root at -3 and a single root at 2. So your graph comes up, goes down, back up. Okay? Double and a single, it's a cubit. Yes, sir? For Mr. Becker? Or from Mr. Becker? Okay, thanks. All right. Now, watch what happens for this graph. For the second graph, I'm going to take the first factor and I'm going to switch it to 2 minus x. But everything else is going to stay the same, x plus 3 squared. Okay? And I'm going to go over it just so you can tell the difference here. And we're going to change that. We'll change it to there we go. We'll make that one a little bit darker when we graph it. What are you anticipating is going to happen to your graph? If anything. Will the 2 minus x change anything? The whole thing, the roots will be the same, single, double will be the same, but your NB behavior changes because if you factor a -1 out of this, it changes your leading coefficient to a negative. So when we hit graph, it's still going to bounce here, still single here, but it's up on the left, down on the right because it's a negative leading coefficient.
Wait, why would your leading coefficient be negative now?
Because when we write this, it should be x minus p, x minus q, x minus r, x minus s. This is not in the correct form. So you factor a -1 out of that parenthesis to get x first, and then minus q second. Then you get the negative out on the other side. It still gives you a root of 2, and you're still single at 2. But your leading coefficient becomes a negative. Does that make sense? Yeah. That's the only thing you have to be careful of here. This is your assignment. Is it 12?